Welcome back, students, to our Chemistry 1510 video notes. In this section, we're going to talk about the Bohr model of an atom. The Bohr model of the atom is the one that you have probably seen in high school science classes. It looks like this. And in this Bohr model of the atom, you have your nucleus, and the nucleus is made up of protons and neutrons. And then you have these layers of electrons that are outside of the nucleus. And these layers can be in energy level 1 or energy level 2, energy level 3, energy level 4, and so on. My circles aren't very pretty. So those layers of electrons or the energy levels can hold only a certain amount of electrons. And you've probably seen that layer 1 can only hold 2 electrons, layer 2 can hold 8 electrons, layer 3 can hold 18 electrons. So that's the stuff that you've probably seen before. The problem is the Bohr model of the atom only works for hydrogen. So what good is it to us? Well, it's a little bit good because it helps us have a basic understanding of how an atom might be set up. The problem is that it really leads people to believe that electrons are orbiting around a nucleus. And that's not true. The electrons are not on this fixed path around the nucleus, but rather there are locations around the nucleus that have particular shapes where electrons are likely to exist. So it does have a very big misconception embedded in it. So let's talk a little bit about the Bohr model of the atom before we move more into what's called the quantum mechanical model of the atom, which is our current accepted theory of the atom. So when we look at this Bohr model of the atom, the one thing that it helps us recognize is that electrons can only be on certain energy levels. So if this stair step is energy level 1, where energy level is abbreviated N, and this stair step is energy level 2, and energy level 3, energy level 4, and energy level 5, the tennis ball, which is the electron, can only live on certain stair steps. It can't hover between two stair steps, and it can't live in two different energy levels at once. So this really helps us visualize that we can only have certain locations where the electron can live. And when the electron falls, remember the electron's the tennis ball, from one energy level to another, what's going to happen is it's going to give off a certain wavelength of energy. If there weren't stair steps, then that electron or tennis ball could be anywhere on the ramp at once, and this would be considered continuous. Whereas over here, we would consider this discrete or quantized. Which just means only certain energy levels or transitions are allowed. One of the best ways to visualize this is in what's called the emission spectrum for hydrogen. So this one's the emission spectrum because you're seeing mostly black. If it was the absorption spectrum, you would see the inverse of this. So let's talk about what an emission spectrum is and how it comes to be. So if we scroll back up to our Bohr model of the atom, I'm going to finish drawing energy level 3, and then I'm going to draw energy level 4, and really I should draw 5 and 6, but I'm going to run out of room. So we'll stick with levels 1, 2, and 3. In an emission spectrum, what ends up happening is here's your electron for hydrogen. It's in energy level 1. When that electron absorbs energy, and that energy in this case would come from electricity, like how when you plug in a neon sign. So that electron is going to absorb electricity. And when it absorbs electricity, what is going to happen is the electron is going to move to a higher energy level. So this would be an absorption. The electron cannot sustain this higher energy level. So what ends up happening is the electron falls back down. Oops, let's try that again. Falls back down to a lower energy level. It doesn't have to fall back down to energy level 1. It could go from 4 to 3, it could go from 4 to 2, but it could also go from 4 to 1. The reason I'm going to 2 is because when your electron transition ends on the second energy level, the energy released is visible light, and that's what we can actually see. So again, what's happening is your electron is gaining energy from the electricity. It's absorbing that energy and going up to a higher energy level. The higher energy level could be energy level 2, 3, 4, 5, or 6. And then it's dropping back down to a lower energy level. And so in this case, I have my electron dropping from energy level 4 to energy level 2. And when this drop occurs, what happens is you see light. All right, so this squiggly line is supposed to be my wavelength of light. And depending upon the transition, depends upon the wavelength of light that you see. So if we scroll back down here to our emission spectrum, what we're seeing is 4 different transitions for this electron. It's going from energy level 6 to 2, 5 to 2, 4 to 2, or 3 to 2, and those 4 transitions give rise to 4 different wavelengths of light. So when you start to consider these emission spectrum, these bands of light are associated with an electron that's losing energy, and that energy is being released as visible light. So this is a tough concept. You'll have to probably go and read a little bit about it, because it's a tough one to wrap your mind around. Let's look at where it's going to be used mathematically. So there's an equation called the Rydberg Equation. The Rydberg Equation can actually calculate the wavelength of light that we're seeing in the emission spectrum. There are 2 forms of the Rydberg Equation. There's a form of the Rydberg Equation where you're solving for lambda, and there's a form of the Rydberg Equation where you're solving for energy. So if you are looking at the Rydberg Equation for lambda, it's going to be 1 over lambda equals RH, which is the Rydberg constant, times 1 over n squared over 1 over n, times the subtraction of 1 over n squared minus 1 over n squared, where the 2 n's are different from one another, and those n's are your energy levels. Now, your Rydberg constant you could have in units of centimeters to the -1 or in meters to the -1. So I'm going to do a problem that uses this first Rydberg equation. So with your Rydberg equation, in this one, it asks you to calculate the wavelength in nanometers of visible light from the transition from n equals 4 to n equals 2. The fact that it's Balmer series is just extra information. Balmer series is just whenever you end at n equals 2, because that's your visible light. So if we look at the Rydberg equation, I'm just going to go ahead and rewrite it really quick. Oops. No, actually that's good, right? Because it's n2 minus n1. No, my brain stopped working. Let's try that again. that doesn't make sense. Both of them are squared. This one's N1, this one's N2. Okay, so I'm used to seeing the Rydberg constant be in centimeters to the -1. So I'm going to use the Rydberg constant as centimeters to the -1. You could also use it to the meters of the -1, whichever one works for you. So I'm used to seeing it as this. Oh, yes. Right about now, you can probably hear a baby screaming. Okay, so if we do our best to ignore the screaming child, what I did was I plugged in my Rydberg constant. I plugged in my two n values. If you aren't told which n is which, then what you want to do is make sure that you're setting this up so that when you do the subtraction, you end up getting a positive number. So most students do better if they don't actually square these and they instead just turn them into decimals, because otherwise I've had some people do some unusual things with fractions. So let's just do that. So now when I multiply these two things, I'm going to get a pretty significant number. Now, one of the things to recognize is that we are in, units of centimeters to the -1, because this is equivalent to 1 over lambda. What you need to do is take the inverse of both sides. So when you take the inverse of both sides, 1 over lambda is lambda, and 1 over this is going to be 4.86272, wow, times 10 to the -5th centimeters. Now, if you look at the question, it wanted this in nanometers. So what you need to do is remind yourself that there are 100 centimeters in 1 meter, and that in 1 meter, there's 10 to the +9th nanometers. So that this way, you end up with 486.272 centimeters. You'll notice that these are whole numbers, so I didn't let them affect my significant figures. I let my Rydberg constant affect my significant figures. Watch your units here. A lot of times, students mix up the nanometer conversion, and they'll end up with an incorrect answer here for that reason. So I think this is a good point to stop. Let's go ahead and be done. Pick up in another video. As always, thank you for your attention. This is Katoni signing out.